This is the continuation of mechanical vibration response under general periodic force. So we have seen the introductory part of this portion in the previous lecture. So let's continue from the point where we stopped. So when the external force F of t is periodic, with the the time period is equal to 2 pi over omega, it can be extended in the Fourier series. So this is the Fourier series expansion. If we consider f of t, the forcing function f of t is equals to a naught over 2 plus the summation of ai cos I omega t as I start from 1 to infinity plus bi sine omega t summation of bi sine I omega t as I from 1 to infinity. Then this the a naught bir, the Fourier coefficients. So the coefficients are expressed as ai is equals to 2 over time period for the given time period. Integral of f of t cos I omega t dt for the integral is on the domain of 0 to time period. Okay, for I 1, 2, 3, and so and b also can be defined like, because here b is the sine coefficient, a is the cos coefficient, so they are related like this, and a naught is the constant. Okay, so the response of the system under general periodic force is considered in this section for both first order and second order systems. So we have discussed what first order system and what is second order system in our beginning lecture. So first order system is a system with the first derivative only, and second order is with like acceleration x dot dot, that is second order system. But first system order may be x dot, that is velocity. So that is the meaning of order. We already discussed it in some lecture before. So what are the first system order systems in our vibration analysis? Let's see some of the first order system. This is a system consisting of rigid bar, which is massless, and rigid bar with having a rigid bar here, which is connected with some material stiffness K, and deflecting y of t from point A. Again, another rigid bar having x of t. So we have different coordinates here, y of t and x of t are, and there may be a relative displacement occur between the 2 points at B, and which is with the base, it is connected with viscous damping. So the governing differential equation for this system is Cx dot plus Kx, which is equal to K times y of t. So actually we can represent it as Cx dot dot plus K times x of t minus y of t, because this there is a relative displacement in between the two. So we can rewrite it as like this. Okay, this difference as this system is redefined as C x dot plus K times x of t minus y of t. This is relative deflection between the 2 points, points B, point A and the B. So Cx dot plus Kx, K times x minus y. So this is the definition of the governing differential equation for this system. Another one is here we have massless rigid bar is here, which is subjected with some forcing function f of t So the reference coordinates x of t is here, and k and c are here. So this can be expressed as c of x dot plus kx, which is equal to f of t. I can represent this as capital F. Okay, so this is first order system because this is in first order only. Again, we have a torsional system here. This is a torsional system. Okay, so there are some bearings are here. These are bearings, and the rotating shaft here, and there is a rotating mass with the inertial property J. And also here it is also supported with some dashpot or torsional damper is here. And also here supported with bearing. Okay, so and applied torque is here. This is a mechanical system. So we can represent it as J omega dot plus Ct, means this is torsional damping Ct omega, which is equal to T of t, means the torque applied at time t. So this is the governing equation for the torsional system. This is torsional system. Torsional system. Okay. So in this case, we have an equation which represents the Fourier series expression. Y of t is equal to f of t, that is the force. So which is equal to a naught over 2 plus summation of ai cos I omega t for I start from 1 to infinity plus summation of bi sin I omega t for I start from 1 to infinity, that is f of t. Now let's consider the first case, this case here. Let's consider this case and let's take this equation as one of the equation. So the governing equation of motion, which is taken like this, and finally, which is as x of x dot of t plus, means just taking these constant values to one side. Okay, so k over c, considering k over c as a. So our final equation will be this one. This is first order equation, x dot of t plus a of a times x of t, which is equal to a times y of t. So this is the governing differential equation in the first order. So let's put it in the expansion, in the Fourier expansion form. So x dot of t plus a times x of t, which is equal to ay of t, which is equals to a naught plus the summation of ai cos I omega t for I from 1 to infinity plus summation of bi sin I omega t as I from 1 to infinity. So, sorry. So in this, A represents k over c, a naught represents a naught over 2, ai represents this a represents ai, and bi represents pi. So these are the definitions. So let's take some example, and based on that example, we can express whatever the situation on that. Find the response of single degree, spring damper system shown in figure A, means this figure. Spring damper system, which is subjected to governing differential equation this. So for that, we have to find the response of the system. Okay, to the Faradic force. with the equation of motion given by 3, means this equation, the previous equation. Okay, so the solution, it can be seen that the right hand side of the equation, you can see this right hand side of equations above are having some constant. That means the a term, which is constant term, plus a linear sum of harmonic sine and the cosine. So these are a linear sum of harmonic terms. Okay, so using the principle of superposition, the steady state solution for this equation can be found by summing up the steady state solution to the individual forcing terms. Okay, how we can find that? Let's see here. For the first case is for the constant term, for the constant forcing, x naught of t plus a times x naught, which is equal to a naught. This is the equation. And solution for this, as we know from our mathematics, x dot plus x is equals to b, some constant b. The solution is what? B over this a. Solution is x of t is equals to, this is just from our linear algebra, so which is equal to b over a. That means coefficient a of this x. So this is the solution. So a naught over a is the solution. Again, the equation of motion corresponding to the cosine term, ai cos I omega t, is xi plus axj, which is equal to a cos I omega t. This is the equation of motion here. Equation of motion. Now, the solution for this, we assume the steady state solution, that is particular solution, which is yi cos omega it minus pi. So how we can select this? We already discussed a lot of topics before, so you can consider from that. And we have here the amplitude constant and the phase constants. Okay, y, capital YI and pi I are the phase constant and the amplitude constant, or the amplitude of this thing. So yi is equals to ai over radical of a square plus omega I square. So from the given, we can calculate this thing. And pi is equals to tan inverse of omega I over a. So this is, again, for the third term, that is sine term, term with sine in our equation, the governing solution is x dot I plus axi, which is equal to bi sine I omega t. This is the equation. And solution, the steady state solution for this is xi of t is equals to xi sine omega it plus minus pi. So here also we have two constants to be determined. So we find these constants like this. Okay. So finally, what you will do? The complete steady state solution for this case is it is the sum of a naught over a, means the solution for the constant term. Again, the solution for the sine term, and the solution for the cosine term and sine terms. This is the solution. Okay, this is the particular solution or steady state solution. The homogeneous solution for the system is given by x of h of t, which is equal to c times e raised to at. So this c is the constant to be determined from the boundary condition, not boundary, but initial condition in our case, because what we are talking are the time derivative of the system, so that it is initial condition. When I say boundary condition, whenever there is some kind of force boundary or displacement boundary or something, then we call it as boundary condition. But here we call it as initial condition. So knowing the initial condition, we can find this C. So x of t, the total solution x of t is equals to x homogeneous of t plus x particular of t. This is the steady state solution, and this is the homogeneous solution. So this is the complete solution for the system. Okay. So for example, in first order, we have only one initial condition. But if it is second order, we need to have two initial conditions. Why? Because in order to satisfy the equation, we need two initial conditions. So the only initial condition in the first order case is x of t is equal to 0 is equal to x naught. So from that, we can find C, constant C here is equals to A naught over A, no, X naught minus A naught over A plus the summation of yi sine pi I minus the summation of xi cos pi I for I from 1 to infinity. This is the initial condition. This is, we call it as initial condition for first order. Initial condition. Okay, great. So let's go to some example here. Example 2. So we directly use this equation. Means most of the terms are already there. So it is not as complex as we expected. So determine the response of Spreng's damper system, similar to the one which we have seen in the first case. So assume the initial condition x of t is equal to 0 is equal to x no, which is 0. So when the initial 0, what will be the response of the system? So the general format of the equation is x dot t of t plus x of t, which is equal to ay of t, which is equal to a naught plus summation of ai cos I omega t for I from 1 to infinity plus summation of bi sine I omega t for I from 1 to infinity. So this is the general form of equation. So from that, we have this x naught, no, x dot, a is equal to 1.5 directly from here. A naught, which is a over 2, a over 2 is equals to this value. Again, the summation of ai from I from 1 to infinity is 4.5. I omega t is equals to only t, means I omega is equals to 1. Similarly here, the summation of bi is 3. Okay, I omega t is equals to 5t, means I omega is equal to 5. So this is the equation directly, the correlation between the general form of equation and the recent equation. So let's now go to take every part of the equation. Means we have 3 constant term, sine term, and cos term. So for the constant term, we have solution x of t is equal to a naught over a, means which is 7.5, because a naught is our a naught is this one, 7.5. Our a is this one, which is a. This is a naught, so that is 5. And for the cosine part of the forcing function, we have solution x of t, which is equal to yi cos omega t minus pi. So then from this x of phi of t is equals to, this is the solution. So on this solution, we can find this constant y. The amplitude constant y is ai over a square plus omega I square. So that is AI is 4.5. What is AI? This thing. This is AI. This is AI term. Okay. And this is BI. This term is BI. Okay. So substitute AI. A is equals to 1.5. Omega, in this case, in the sign, this case, omega is 1. Okay. Here, omega is 1. Okay. Substitute it. Finally, we can get 2.4961. And pi I, the constant pi I in this equation means the phase angle, which is equals to tan inverse of omega over A, which is 0.588 rad. So this is pi. Again, for the sine part of the component in the equation, we have a solution xi plus 1.5 xi. This is xi, sorry. So which is equals 3 sine 5t. So the steady state solution for this is xi of t xi sine 5t minus pi. Still we can find, we have to find this one and this one. So these two terms are found as 0.5775, that is xi, and pi I is 1.28 rad. So substituting all these values to the equation, for the main equation, this is the general equation, what we have is, this is 5 plus, that is 5, we already found it here, this 5. Again, summation of this term gives us 2.496. Okay. Then cos t minus 0.5, because this pi 1, we consider this as pi 1. Okay. Pi 1 is equal to 0.588. And here we have pi 2. I simply call it as pi 2, that is 1.28. So we substitute these values here, and this is the general equation. Now, just substituting the homogeneous equation also, C is raised to AT on this equation. What we can get? This is the general equation. And now apply the boundary condition x of 0, which is equal to 0, means from this we can find C, which is minus 7.483. So applying this value to this equation, we can get the final equation. Okay. This is all about first order system. Now let's see second order system. So second order system, there is the inertial part or acceleration part also included on the system. Okay. So let's see this system. We have mass. Previously it was massless. Okay. Here we have mass. We have spring or and we have dashboards. So the equation of motion for this system for forcing f of t, which is equal to mx dot dot plus cx dot plus kx is equal to f of t. This is, sorry. And for the torsional system, we have rotor having torsional inertia J, and also torsional damper CT, and there is a torsional stiffness KT here. Okay, so this is a torsional spring, torsional fluid media here, and torque is applied here, and the deflection, rotational deflection theta of t is there. So the general equation J theta dot dot plus CT theta dot plus KT, which is equal to T of t. So this is second order because we have this thing. So let's now consider this second order, and let's go to perform some activities. Okay, so the general equation of second order dynamic systems mx dot dot plus cx dot plus kx is equal to f of t, which implies uh, this m of mx dot dot plus cx dot plus kx, which is equals to a naught over, means this is the Fourier expansion of the forcing function. Okay, that is periodic forcing function. Okay, so this is the general equation represented in B. Now, the solution for this, how we can tackle this solution, this system. First, let us break the system into three components with the constant a naught over 2. Okay, mx dot dot plus cx dot plus kx is equal to a naught over 2. Okay, with the sine function and with the cosine function. And for each of these function, give solution. This is a solution for the constant one. X particular of t is equals to a naught over 2k. 2 is this one, k is this term, 2k is the solution for the constant part. Again, for the cosine term, we assume cosine solution. Okay, we assume cosine solution for the forcing function with cos. We consider similar cosine term, so that is the solution for the particular solution for this term. Okay, again, the sine component of this equation, we have also solution here. So this is the solution. Okay, in this ai cos I omega t for I from 1 to infinity, we assume ai over k, okay, over radical of 1 minus I square r square, the whole square plus 2 zeta I r square. So here I is the number of that iteration, that 1 to 3. Okay, this 1 to 3 thing to infinity. R is the frequency ratio. That means natural forcing frequency over natural frequency ratio. Okay, so pi I r, the tan inverse of 2 pi I r, 1 minus I square r square. Okay, so this is a way how we can find solution. Therefore, the complete solution, the steady state solution for this case is similarly x particular of t is equals to a naught over 2k plus summation of the cosine solution and the sine term solution. Okay. So in order to understand this equation clearly, let's take one example, that periodic vibration of hydraulic valve. So I mentioned this part in the early discussion. So we have here there is a channel or chamber, pressure chamber. There is a pressure which apply from this this mass to here, okay, and the diameter of chamber is given that 50 millimeter diameter, okay. So this is the mass which is attached to stiffness and the damper, having a motion x of t, and the forcing, the pressure P of t is defined here. Okay, this is the graph of pressure in Pascal and time in second distribution. So we have this type of ramp loads, okay, periodic ramp loads with the period of the time period of 2. Okay, this is period 1, 2. In so to complete one period, it takes 2 seconds. So the line from 0 to this point defined as 50,000 t, and this line is defined as 50,000 times 2 minus t. Okay, this is the definition of the line. So we have to define this region into two. Okay. And the area is calculated as pi d square over 4, which is 625 pi millimeter square, or we can convert to the metric system. Okay, that depends on our calculation. So this is the whole system. Okay, all parameters are given here. Okay, now we can do this. So the first expression f of t for this case is this, that is expression of the forcing function. So now what is going on that this is the constant term, and the sine and the cos term means the a terms are a1 cos omega t plus a2 cos 2 omega t plus a3 cos omega cos 3 omega t plus so. And the b term means this term b1 sine omega t for I1, b2 for I2, b2 sine 2 omega t for I3. It will continue like that. So observing from the figure B, means the previous figure, f of t is given us from this figure. We can define this function in separate regions. So f of t is equal to 50,000 t times a. A is the area. Okay, 50,000 AT for 0 to time period over 2. And it is 50,000 a times 2 minus t for t half of time period to full time period. So there are two distinct regions. So one period, half of for this region and for this region. Okay. So now what you can do, we have to do some analysis for A1, A2, A3, A4, B1, B2, B3, B4 for A0. Okay, so what we can do now, this is the forest coefficients can be determined from this relation. Okay, so A0 is equals to 2 over 2 as a whole in bracket integral from 0 to 1, integral of the first term of the given function, means our function f of t is equals to it is 50,000 AT for 0 to 1. Okay, and it is 50,000 A times t minus 2 for 1 to 2. Okay, 1 to 2. This is the expression 2 minus t. So from this, what we can get, A0 is equals to this value. A is the area. Okay, again A1, which is the cosine term. So we calculate it with this is the representation from 0 to 1, and this is representation for 1 to 2. Finally, what we can get, minus of 200,000 A over pi square. Okay, it is not like this. There is 1 0 missing here, and 1 0 is missing here. So 200,000 A over pi square for I1. For I2, it is 0. Means, and for I3 it is minus of 200,000 A over 3 cube pi square. Means for I3, so that it represents 200,000 A over I r square, I pi square, the whole, the representation. For I, odd portion of I, it is not, because for even part of I, it is 0 here. Okay, so like that. Again, for B case, B1, we calculate it and finally we get 0. B2, we get it 0. B3, 0. That means the sign part of this equations is 0, so that every B3, B4, B5 will be 0. But in this case, the even terms are 0, but odd terms are having values of this kind of expression. Okay, so yeah, that is what. So by considering the first three harmonic, the forcing function f of t can be represented as 25,000 minus 200,000 over pi square cos omega t minus 200,000 over 3 square pi square cos 3 omega t. So finally, someone can represent this equation in general form, actually, in general form. But let me leave it as it. So x particular of this equation becomes, because this is the solution for this this type of forcing function. So the solution 25,000 over k minus 200,000 over k pi square over these quantities cos omega t minus pi 1. This is for the first term. This is for the third term. And the fifth term also will continue. Okay. That multiplied by a. So this is a general solution. So let's now, we have numeric values given in the equation. So let's consider the natural frequency, k over m, because it is already given there. So 2,500 divided by 0.25. So this is the natural frequency. The forcing function 2 pi over time period t, which gives pi rad per second. And the frequency ratio is omega over omega n, which is 0.03146. And the damping ratio zeta is equals to c over 2m omega n, which gives us 0.2, which is under damped case. Okay. So the phase angle is directly pi 1 is this one. And this is pi 3, sorry, this is pi 3. Here it is pi 3, and here it is pi 1. So that pi 3 is equals to tan inverse of 2 times 3 zeta r over 1 minus 3 square r square. So which gives us 0.03805. And the solution can be just substituting these values, we have this solution. Actually, we can put here this solution, this value here, and every terms will be complete. Then this is the final solution. So we'll see response under non-periodic force in the next lecture. Thank you very much for watching this video. It may help you a lot. So thank you.